very appreciative to be up here and moderate this panel on quantum sensing and networking. Just want to do some quick introductions for myself and the panelists. My name is Jeff Whalen. I'm the CEO of Magnetics Corporation. We do technology development and economic development in commercial superconductivity and magnetism. And really, we found our way, I was talking to Jim earlier, found our way into quantum through superconducting magnets in dilution refrigerators. And it's been just a great journey since then. And now we have moved forward into a development of a superconducting quantum data center in Central Florida at our cryo site. So very appreciative to be here, and I'll pass it to Jim to do a couple minutes of intro, please.
Sure. Hi, everyone. Is my mic on? Yeah. I'm Jim Ricotta. I'm the CEO of Aliro. We are one of the first companies that has been in quantum networking. We were founded 5 years ago. We spun out of a physics lab at Harvard. And we're focused on some of the use cases, very important use cases for quantum networking that you've heard about already today. Creating unbreakable security using quantum physics, networking together quantum computers to solve some of those big problems that you wrote on the little paper, and also networking quantum sensors, which has very important strategic implications for things like positioning and timing and sensing beyond what we can do today. So it's a very exciting field, and we're happy to be one of the leaders in it.
Good afternoon or good morning. My name is Austin Capers. I'm the president of Scientific Instruments. We are a West Palm Beach-based cryogenic engineering company, and we focus on thermal management products for ultra-cold temperatures. I'm also a Palm Beach County resident and born and raised here, so thank you for having me.
Yeah, hi, I'm Ron Walsworth. I'm a professor at the University of Maryland in physics and electrical and computer engineering. So I'm one of the people not doing a good job training enough quantum physicists. We'll have to speed it up. I'm an academic. I've been, my area is in quantum sensing, precision measurement. That means measuring and imaging things using quantum systems. I've also been involved in commercialization as an academic co-founder and advisor to a lot of deep tech and quantum companies. And I'm the founding director at University of Maryland of the Quantum Technology Center, which is an active effort to bridge the gap between academia and commercialization to mature the technologies, train the next generation, all these sorts of things, and translate those technologies out. I'm a quantum sensing person, but we include computing, quantum computing, networking, communication, materials activities. So kind of like 360 quantum.
Thank you all. And the overarching theme of today is really that quantum is here now, and we have to embrace it or we're going to get left behind. And the notion of quantum sensing and networking, I think, really kind of needs a baseline of understanding for everybody. So this question is mostly directed for Jim and Ron, but could you speak a little bit about what is quantum networking and sensing? How can the general audience and the general public look at something and say that's quantum sensing and networking or that's not?
Yeah, so a key point is that of the different quantum technologies that you're hearing about, quantum networking is the closest to commercialization. In fact, we've heard already that there are production level quantum networks in China, and there's some here in the US also, and more on the way. Basically what we're talking about is using qubits. In the case of networking, photons are the preferred qubits because they're particles of light that travel very easily through the telecom fiber that we have all over the ground in our country and the world. They also can be used, they also can be transmitted via satellites. So using entangled photons, you can connect two parties, and as we heard, you can exchange a secret key without any possibility of it being broken or intercepted. You can connect quantum computers with qubits to create a super powerful quantum computation capability. And you can connect, there already are, as Ron is going to tell us, a lot of quantum sensors that are deployed out there. And if you can network them together with qubits, with entangled photons, you can get super high resolution and quality and imagery that you can't get today. So it's all about using the infrastructure we have today, the fiber in the ground and the satellites in the air, to transmit not just bits, which we all know how to do and have been doing, for the last 30 years, but now to transmit qubits to get these new capabilities.
Yeah, and so as I mentioned earlier, quantum sensing is using quantum systems to measure things, RF fields, magnetic fields, temperature, pressure, radiation, chemical concentrations, etc. And there are a lot of successful, already deployed, let's call it mid-late 20th century quantum sensors, atomic clocks, for example, which are on board the GPS satellites and synchronize everything from your phone to financial transactions, navigation, etc., are using the quantum properties of atoms in those atomic clocks. That's why they're called atomic clocks. But there's a whole bunch of kind of next generation 21st century quantum sensors that are coming online and that have diverse applications. I particularly specialize on certain solid state based systems which have defects in diamond, silicon carbide, things like this, can do remarkable things that no other technology can do. And I think one of the things about sensing and networking, they work together with computing, and quantum computing is of course super exciting, but you often, to make a useful networking or sensing system, it doesn't often have to be as large or advanced as a quantum computer to become better, let's say, than a supercomputer, which is why a quantum sensing tool or networking tool can at an earlier stage do commercially useful things. The Nobel Prize yesterday in physics was announced, and it was for physics developments in the 1980s that showed that superconducting loops, squids, old school versions back then, the low temperature ones, you could have collective macroscopic effects that allow you to use them usefully. And certainly that forms the basis for some of the quantum computing architectures. But earlier than that, people started using those squids for all sorts of sensing things. Biosensing, sensing magnetic fields from brains, materials, etc. So that is an example of basic physics that's leading to exciting quantum computing platforms, but along the way come high impact applications in sensing. I think Jim could say similar things about networking.
Thanks, Jim. Thanks, Ron. I think what is happening through this event and what's happening throughout the state of Florida is really leveraging a lot of the existing ecosystems. And Austin, you and I, both of our companies are in this state, and we've been established here for a long time and are kind of familiar with the ecosystems here. Adding a quantum ecosystem in the state of Florida feels so natural because so many of our ecosystems are already deep technology. Things like our Space Coast and the Lambda Rail project, all of our military bases, the MAGCORP cryosite, all of our financial districts in South Florida, all of our airports and seaports. These ecosystems are all opportunities for quantum integration. And I think that within the state, there's this question, how do we identify those ecosystem opportunities for quantum to become important in all of these existing Florida ecosystems? So, Austin, would like your thoughts on sort of how you've been able to integrate your company into these Florida ecosystems and thoughts on where you see identifying those opportunities in quantum.
Yeah, thanks, Jeff. I think we continue to foster these cross-sector alliances, from space operations to military and intelligence, finance and trade, and our universities to continue the collaboration and grow awareness, for what the future is. You mentioned, like, just the word quantum, sounds futuristic, but like Jeff said, it's here, it's now. So, my company specifically is, a child of the space, ecosystem. In 1967, our founders created a novel sensor that was used on the Saturn V rocket and the lunar extraction module. It's because of these ecosystems that companies like mine exist today. So continuing to have, doing what we're doing right now, talking about the issues, the challenges, and the solutions so that we can create a better future.
Yeah, I think it's an incredible opportunity. We were at dinner last night, and I was talking to some of the folks there about what AI has done for certain applications and industries. MRI, one that's near and dear to my company's heart because it's a big superconducting magnet, and what AI has done for imaging in MRI. And it led to this discussion, how can we even conceive of what quantum will do to an industry like MRI? How can we take what we see in artificial intelligence that's being used to operate fusion energy machines and ask the question, what will quantum do to disrupt how those machines run? So I think, Austin's example there of how the space industry and how that developed the opportunity for his company, I think we're going to see ecosystem integration, especially in the state of Florida, across all of these different applications where we see quantum enablement of a next generation system that already exists, like an MR or a fusion machine. So thanks, Austin. Really appreciate that. Jim, this question is mainly directed for you, but these technology nodes have been used across so many different sectors. They drive innovation, they bridge the gap to commercialization, and there's already a lot of quantum nodes in the United States. Elevate Quantum out in Colorado and New Mexico, the Chicago Quantum Exchange in Illinois, the Brookhaven Stony Brook Network in New York, the DC QNet in Washington, D.C., and even just recently, the Roadrunner Venture Studios that was announced in New Mexico as well. And there's more, all focused around quantum. And Jim, the question to ask is, how do we accelerate innovation programs and accelerator programs in the state of Florida to interact with all of those other nodes so that what we end up with is the world's largest network of quantum integrated nodes? How can we see that vision?
Yeah. As I said, we've been at Aliro, we've been in quantum networking since the beginning of it, 5 years. And what you see, if you compare to the way the internet was developed, you saw in the 70s and 80s islands of networks in different parts of our country, and then they got tied together as the technologies got a little more mature. And that's what you're seeing with quantum networks. So as you said, there are regional networks in Chicago, in DC, in New Mexico now. There's one of our first customers is EPB, which is in Chattanooga, Tennessee, and they're connecting up with Oak Ridge National Lab, which is just 100 miles up the road. So what Florida can do, and as was pointed out, you have a lot of resources here that can enable building a networked quantum hub. You have the Lambda Rail fiber. Yep. You have expertise in satellites. One of our most recent customers I can announce today is Boeing, who is doing a quantum satellite project based on the Aliro software products. So you can build another regional quantum hub, including networking and computing and sensing. And given the geography and the amount of talent that's here and the history that we've heard about, it could be the biggest one of any of these that exist today. And then you're well positioned for when the technologies get a little maturer, you get the quantum repeaters that Marco was referring to, and then you can start to connect not only to different parts of the country, but using satellites connect to Europe and Asia and that sort of thing. But it all starts with having, using the fiber you have in the ground and the technologies that exist with a little bit of, the market signal, which they talked about in the last session, which I think is very important, and building that kind of a hub, which is very, very doable today.
Thanks, Jim. Ron, do you want to add anything to that?
Yeah, I think with regard to the sensing side of things, the quantum sensors are typically physically small, right? Might be a tabletop instrument, or heading towards handheld instruments, maybe someday in next-gen phones and things like that. And so it's easier, oftentimes, for a state that wants to really be strong in that area to relocate the companies, early-stage companies. They're not having to relocate very large computer systems or networking systems. So I think the challenges for integrating quantum networking and sensing will be somewhat different in terms of an ecosystem. So I'd say for the sensing, it's typically smaller devices that are nearer term, that companies typically won't be as capital intensive to get to the market, right? And there's diverse sets of applications. So though networking, sensing, computing, et cetera, all use variations of similar platforms, photonics, ions, superconducting, solids, atoms, et cetera, they're configured in different ways for different types of applications that have strengths, pros, cons, challenges, different challenges. I think a really good play for a state like Florida is one to be a leader in at least some of the frontier the hardware developers, but the integration and the application space, right?
Such great points, and I couldn't echo more strongly the sentiments that were given in our keynote this morning about how massive this opportunity is to establish this state of Florida as the largest quantum node in the United States. So really appreciate the thoughts. Ron, this question is mostly directed for you, but we all have lived our lives with sensors and networks all around us that were not then nor now really considered necessarily quantum. Fiber optics and cell phones and satellites and even the internet and so many more, on the networking side. And then even simple things like the float fuel sensor in my weed eater, or these complex aviation-based sensors that are used in commercial flight. How can the general public, how can the audience here be able to distinguish? How can we look at something and say, I know that's a sensor. Is it a quantum sensor or is it a traditional sensor? Is there a way for me to simply be able to make that determination, or do I need to have like a really deep understanding of what quantum sensing and networking is to be able to distinguish the two?
I'll be talking a bit about a metaphor in a second to try to make
Excellent.
that point. But I'd say in the end, for the average person, if they're interested, we can go deep and teach you all sorts of things. But in general, you just want to know, is a computer, a sensor, a network better for your need? Is this a good deal? Are you getting better performance, far better performance in some way? And the promise of quantum generally, whether it's measuring things, communicating and networking and computing, isn't just a little bit better, it's dramatically better performance. Things that can't be done today, typically. If you're only getting 10% improvements after all this investment, that's not going to be really so great. So it's dramatic difference. Okay, metaphor. You heard from Professor Nettles when he was talking about the challenges in trying to solve various protein structures and understand their function and whatnot, is that everything around us, in our bodies, in the materials, the phone again, the air, is made up of atoms and molecules, nuclei, electrons. They're fundamentally quantum systems. Mostly in our everyday lives, we don't have to pay attention to that. Our crude fingers and our eyes are too fuzzy to see the atoms and molecules. We can mostly ignore it for most things, but not if we want to cure disease, not if we want to solve a series of other problems or communicate perfectly safely. Then we need to deal with the universe as it is. It isn't this fuzzed out version that we live in our daily lives mostly, where we're ignoring atoms, molecules, quantum effects. It is quantum from the bottom up. Right? So it's time to grow up as a species and be able to deal with the universe as it is. So the metaphor is this. In the 20th century, starting in the early 20th century, moving on, we humans figured out that atoms, molecules exist, and they learned the rules of quantum mechanics, quantum physics. In fact, this is the International Year of Quantum, because 100 years ago, 1925, was when Heisenberg and Schrödinger first developed the first early quantum mechanics theories. And throughout the 20th century, as we learned those facts, we developed technologies like computer chips, lasers, MRIs, et cetera, atomic clocks, which take advantage of quantum effects, but again, do it kind of crudely. It's sort of like having a bunch of Legos. Here's the metaphor, finally. Little Legos you want to build something out of, and you got a big pile of Legos, but you got winter mittens on. And you can't take them off. That's humans in the 20th century. We know the Legos are there, so all you can do is kind of pile them up. Maybe you can get the green ones and the red ones to be separate. So that's kind of useful to make a pile of Legos, I guess, if you're a kid for something. But if you want to build the Death Star or build some fancy airplane out of your Legos, you need to take the mittens off, use your fingers, and control each Lego and put it together the right way. And so now, finally, with the developments, was rewarded with the Nobel Prize yesterday, and 13 years ago, the Nobel Prize that was shared by Dave Wineland, who together with Chris Monroe, co-founder of IonQ, made the first quantum gates work. in the 1990s out of using ion traps. Now we've developed the tools, we humans, to use our fingers, take those gloves off, and build fancy technologies, right? So to the general public and to everybody else, we are entering an era where radical new capabilities are starting to become real, because finally we can deal with the universe as it is. Right?
I love
That's
it,
how
Ron.
you know. That's how you know, because things have just gotten a lot better, a lot cheaper, et cetera.
Taking the gloves off and building the Legos with some dexterity. I love it. Next question really is focused around supporting technologies, and I think it's interesting to look at an industry like quantum and recognize that, similarly to other deep technology industries, that qubit or that QPU can't just sit there on the ground and operate. There's a whole host of supporting technologies that are required to get something functional out of that QPU. And cryogenics is not something that's used in all forms of quantum technology, but certainly in many of them, it's a key supporting technology. And if that QPU is required to operate at ultra-low temperatures, it's not an option. The cryogenics is critical for it to function properly. And when we look at the field of cryogenics, in the beginning, it was really just dunk it in liquid helium, dunk it in liquid nitrogen or liquid hydrogen. Be the case what it may, it's just taking a bath in cryogen. And we have moved into an era of cryocooling that commercially viable systems that need cryogenic conditions are realizing profitability that never could have been touched with simple immersion cooling in liquid cryogenics. And Austin, this question is really for you, especially given how much your company works in cryogenics, but we've got a whole host of these supporting technologies, including cryogenics, and all of them impact the final profitability bottom line for that OEM. They all are going to stack up on the final cost of goods sold. And where do we kind of see these opportunities for leveraging these recent advancements? Cryogenics is really just an example. Thermometry, second generation superconductors like Rebco, where do these enable quantum profitability in this quantum industry? And how can we think about these things in ways that they could even potentially support non-cryogenic quantum? So Austin, really would appreciate your thoughts on how we can leverage these recent advancements in supporting technologies, especially speak to thermometry as it applies to the quantum industry.
Yeah, absolutely. The quantum, topic is just taking over our industry and kind of revived it. Every conference we go to, American physics, cryogenics, superconductivity conferences, it's dominated by quantum talks and development. So that is driving advancements in cryogenic thermometry with temperature sensors and electronics, the superconductors, the Rebco, to the cryocoolers and the dilution refrigerators. So everything is getting better, because of this quantum race, and we're glad to be a part of it. Yeah, that's about all I have.
Thanks, Austin. I was talking to Jim in the side room right before we got up on stage, and last week the HECI device was launched into space, and it's a small Rebco superconducting magnet, and the cryocooler for this magnet is about the size of a soda can. And I was blown away that you could reach cryogenic temperatures on a few watts with this thing that literally could fit in your pocket, when 5 years ago, that same cooling power would come from something that would be the size of like your home refrigerator. It's incredible to see these types of advancements, and especially in the field of second generation superconductors like Rebco, and what that's doing for industries where they were served by first generation superconductors, or they were not served at all by superconductors but now can. And I think what we're moving into in quantum is a very exciting era, because we're in the Wild West. It's forging that basis of our first understanding of what the technology can do, but the thought to say, what is this going to look like 5 or 10 years down the road, is perhaps even more exciting. Ron, do you want to add?
Well, I think Jim probably can say this too. The subsystems that are needed to make a quantum network computer, sensor, are many typically, and each of
Yeah.
those need optimization.
Yeah.
And we need a supply chain that's overwhelmingly in the US and a few friendly countries, let's say. A lot of advancements, cryogenics have made amazing advancements. Many materials have, but some, and light sources, but some have a lot of work still that's to go, and I think there's a lot of opportunity for Florida and other states in that space too. Not just the endpoint hardware, like I said before, but the supply chain, all the components, and the use cases.
Thanks, Ron. I'm glad you mentioned supply chain because this question is really very near and dear to my heart. What we see happening in quantum right now, including quantum networking and sensing, is really having its potential first major impacts in the areas of national and economic security. It was mentioned several times earlier this morning. And many of us are watching or have lived firsthand what we experienced in much more mature supply chains like rare earth permanent magnets. And what we saw happen was decades, literally multiple decades, of a lack of care for the impacts of what that supply chain meant that it was offshore. And there was this reliance and this complacency that was developed where it undermined that national and economic security so long and so deeply that we couldn't just wake up one day and say, oh my gosh, we're so vulnerable, let's fix it right now. It's a problem that was not only difficult, but once it became glaringly obvious, it wasn't quick to solve. And it's interesting to look at quantum and say, how can we avoid getting into that situation? I think, I've mentioned fusion energy. I think that's another good example of a global race similar to quantum, where if the US takes an approach of being aggressive and maintaining competitiveness from the outset, then we avoid a situation like we're in right now with the rare earth permanent magnet supply chain. And taking that similar approach to quantum is going to mean that we need to stay at the forefront. I'm not recalling now what was mentioned earlier, but we have to meet it head on. We have to maintain competitiveness or we get completely left behind. And the question, and really this is to everybody on the panel, what kind of key decisions do we need to make now, in your opinion, to keep the U.S. competitive, to maintain our national security as quantum becomes a daily reality around us, and what can we learn from like these past mistakes that these were the hard lessons learned, like in the rare earth permanent magnet supply chain, to not end up in the position that we are in that supply chain purely from this lack of attention, lack of funding? How can we drive this industry forward, especially in the area of investment, and avoid those past mistakes? So really, I'd open that up to thoughts from any of the three of you.
Jim, you want us to go first?
Yeah, Jim.
Sure. So if you Google quantum companies in the U.S., you're going to have a very long list, right? So we have innovative companies in quantum computing, quantum networking, quantum sensing, and all the supply chains that are needed to put those systems together and make them work. So it's just really, again, that demand signal that we heard about on a previous panel. Some of the funding that we've got from governments and states and regions, just building basic, investing in basic infrastructure, quantum networks, quantum computing centers, obviously, some educational centers and resources. That's going to kind of kickstart the industry and prevent the hollowing out that we saw with your example, like the rare earth industry. So it's just really, spending the money and letting these companies continue to grow and produce the innovations, and use cases are being found, and they're very critical to industries that are very important to us, like finance and pharma and energy and others. So.
Yeah, I'd say, to echo what we've heard many times, a larger demand pull, demand signal, maybe at the state level can do it too. That is the main thing to get that whole cycle working well. Because right now, even with the sensors that are out there in the market and the networking systems, there are some customers, but we need to get that going so that the efficiency up the supply chain can get improved, and the small or medium-sized companies who are developing specialty photonics, specialty materials, specialty cryogenics can have the demand signal to them right? From let's say, the quantum hardware builders. That'll be key. Then, what we can't do then, of course, you could look at the case of Silicon Valley, right? Why is Silicon Valley called Silicon Valley? In the 1950s, 60s, 70s, Fairchild, later Intel, and these bunch of companies purified silicon, the material silicon. There's competition with germanium and other materials, but in the end it was silicon from which computer chips were made. And they dominated the world. All the innovation was there. All the biggest companies were there. But now that's no longer the case. Intel struggles and needs government support, et cetera. There's big companies located in Silicon Valley, but they're mainly doing the design and outsourcing a lot of the hardware development overseas, which creates the rare earth magnet cases particularly bad, but also creates other kinds of supply chain issues and fragility for our nation. So therefore, though I would recommend demand signal with governments, state and federal playing a key role, I think there needs to be a healthy interaction between the commercial sector and U.S. government, both state and federal, so that we don't just maximize short-term profits by outsourcing in ways that are going to put us at risk long-term. I'm not suggesting overly regulatory things done legally that require too much, that limit the private sector in terms of what they're going to do. I would call it a constructive dialogue so that we don't end up, and partnership, so we don't end up outsourcing too much.
Yeah, it's really interesting to actually, I'll ask a follow-on question because I think it's really interesting to look at that rare earth permanent magnet supply chain and see what's happening now, not just in the use of the supply chain as an economic weapon, but instead the US government's decisions for DFARS and ITAR compliance that's directly applied to where those magnets came from, regardless of where in that processing portion we look at, whether it's saying where was it dug out of the ground, where was it reduced to permanent, to fully reduced metal, where was it strip casted into a block, where was it magnetized. That entire supply chain is scrutinized by the US federal government, so much so to the point that on January 1st of 2026, you must show full US and allied provenance of every single permanent magnet that becomes DFARS compliant. So for a DoD application, it does not matter at any stage where that magnet was being produced, mined, magnetized, anything. It must be proven provenance to U.S. and allied supply chains only. And with electronics, it's very different, right? They're classified differently under DFARS and ITAR. So I can see this potential gap in maintaining provenance and resiliency of a supply chain in quantum, especially for DoD applications. So the follow-on question that really just came to mind, it's not on our list of preps, I'll throw you the curveball, but how do you all feel as a panel that the US government is doing when it comes to policy around provenance and supply chain resiliency when we apply it to quantum? And we look at how strict, Ron, to your point, how strict it is in rare earth permanent magnets. I guess the question is, are we doing a great job? Are we falling behind, or are we somewhere in the middle?
My experience has been that it's not the healthy dialogue and partnership that I'd like to see. It either goes from too lax and nothing's being done, or bam, too strict, and without the understanding that, especially in a nascent industry, many of the companies, small and startups, et cetera, they need assistance. We want good partnerships where there's willingness to do things the right way that help to make that happen, and a dialogue. I know it's hard for government to think on how to be a partner. Maybe states can do a better job than the federal government on these sorts of things. That's been my experience.
Austin, do you have any thoughts? I mean, your company deals a lot with the DoD space applications, but thoughts on quantum?
The access to that type of business is really difficult if you haven't done it before. But there needs to be more partnership from the federal level, and the funding needs to get approved. But and also the tariff situation is really hurting us as well. We're a small business, and that decreases revenue, which decreases eventually R&D into some of these new technologies. So we need better cooperation for sure.
Jim, do you have any thoughts on where we stand on U.S. policy in quantum, applying it to a future perspective on what that supply chain is going to look like a few years down the road from now?
I agree with a lot of the comments that we have to get ahead of the curve this time and be proactive, understand that this is a critical race. It's got to be won. Some of the organizations are, one of our biggest customers is the U.S. Air Force, and they are very forward-looking when it comes to quantum and the supply chain and the ecosystem. But I think more parts of the government have to get in the same, engage with us and get up to speed.
Great thoughts, and I agree with that. And we have a few minutes left while we have our panelists up here, and I'd like to open it up to the audience. I have a few backup questions, but if you all have some questions to ask of myself or the panel, we'd love to welcome those now. Go ahead, thank you.
Question for Jim. How would you compare what you all are building to perhaps what NVIDIA has been able to achieve with CUDA? Do you think it's an apt analogy? Do you think it's a stretch?
So the question was to Jim, how does what he's developing at Aliro kind of compare to what NVIDIA is doing with the CUDA-Q platform?
I think it's a reasonable analogy. We are a software platform company at Aliro, and we picked that approach to quantum networking because, we have not just quantum physicists in our company, but we have networking people like myself who have spent decades, building the products that run the classical internet at places like Cisco and Juniper and others, Arista. So we built a software platform that can adapt. The application sees the same thing, but the hardware can change, because one thing about a new industry, a new field like quantum is things are going to be, there's a lot of innovation, things are going to change rapidly. So you've got to have an insulation layer, and that's kind of what CUDA does for the AI developers. As the hardware changes underneath, you can keep the same API. So I think I might have to talk to my CMO after this. I think it's a great analogy. Thank you.
I think I saw one more question in the back there. Yes?
So you mentioned the rare earth metal supply chain being a concern. Are there other materials or industries that we as a country aren't purposefully developing, knowing that we're going to consume them in a scarce resource environment?
So the question was, are there other materials that we look at in the supply chain where there could become scarcity and we could be exposing ourselves to supply chain risk outside of rare earth minerals for permanent magnets? And I love the question because every year the list of critical materials is updated and republished, and there's always sort of a longer list of every type of material that you could class as critical or not critical, and there's a cutoff. And right there at that cutoff, there's always the materials where they might jump on the list one year, get dropped off the list next year. And I noticed materials, a couple of them that made the list that weren't on there last year, like yttrium. And I sit there and I wonder, especially in our world at MAGCORP, is that being driven by second-generation superconductors that are made from yttrium, barium, copper oxide, and scandium for alloying? I think these types of materials, these types of minerals and elements as metals have a serious importance. I kind of, and from the panelists, I love your thoughts, but I kind of would sit here at this conference today and say, what are the critical materials and their supply chains that could impact quantum? Not just in terms of QPUs and materials that are used to create them, but all of those supporting technologies as well required for QPU operations. So I don't have a distinct and specific answer for that, but I do think it's a really intriguing question because it goes along with what we were speaking about earlier. How can we be at the forefront and prepared so that we don't end up in the same situation that we are in the rare earth permanent magnet supply chain? But I'll kick it over to the panel for thoughts on that question. I think it was great. Go ahead, Ron. Okay.
In addition to actual basic elemental materials, there are fabricated materials and components.
Yes.
For example, quantum-grade diamond. Many of the technologies I work on involve these atomic scale defects in diamond, which are very good for sensing electromagnetic fields and all sorts of quantum sensing applications, also networking. Some of the, like the company LightSync that was acquired by IonQ is based on defects in diamond as an example. So these what do I mean by quantum-grade diamonds? They're not the diamonds dug out of the ground that you've heard about that maybe are sometimes made into gemstones. They're fabricated diamonds, still the same at the elemental level, made out of carbon, but with a controlled, high quality control of the material, so low impurities, low strain, and then the desired defects, which have quantum properties in them, even at room temperature, placed just where you want them inside the diamond. Okay. There are several companies in the United States, small companies. The best company, though, in the world is a UK company, a British company called Element 6 that's related to De Beers. And they're larger, but none of the companies, there's some other few companies in other parts of the world too, none of the companies yet are able to produce the quality of diamond that you need consistently and at scale. Why? And certainly not in the US, because of this not enough demand signal yet. So instead it's like grandma making a bunch of cookies, and each one comes out about the same, but they're not exactly the same. And that's okay, because you can cherry pick the best one or the best diamond for early stage when you're selling small numbers of products. But if you want to scale up, it's not there. So you talk to some of these companies, they say, we'd be happy to do the very large amounts of material R&D that's needed to ultimately scale up like Silicon Valley did 50 plus years ago, but it's going to be, any material development is going to be very expensive, right? So that's not quite the same as a rare material that's found and dug out of the ground. It has to be made by humans, but it's a similar sort of thing in that we don't have the capabilities there and some other materials in photonics, many laser sources, et cetera, because there isn't yet the demand signal to fund the development of those things.
Thanks, Ron.
Yeah, I was just going to add, I don't know anything in the supply chain perspective that, is a concern that we're not doing anything about. But, for us in the world of cryogenics, it's what comes to mind is helium and helium-3 and the lack of those resources. So eventually we're going to be mining on the moon, I think. But that's a big concern for us. And we've installed, a liquefier to recapture about 90% of that, but eventually we're going to run out. So
that's a great point on the helium supply chain. We've got time if anybody has one final question for any of the panelists. Go ahead.
Yeah, being that this is about quantum sensing and quantum networking, I'd like to hear more about the intersection there and entangled quantum sensor networks. What do you see as the nearest term applications, use cases, and benefits?
Great question. Asking about the intersection of quantum networking and quantum sensing and where we see the good use cases and applications. I think, Ron, you and Jim probably have some thoughts on this one.
Yeah, I think there will be areas in terms of advanced PNT, navigation timing, precision navigation, precise navigation and timing, space-based, early on, airborne. Agree, Jim? Does this make sense to you? Where it's... Yeah.
It does, yeah. One of the applications I hear about a lot is one of the strategic concerns is, GPS is what's relied on today for positioning and navigation. What if GPS is either degraded or completely denied? And so networking atomic clocks, which is a form of quantum sensor, is a way you can do positioning and navigation without GPS. That's one thing I hear about a lot.
Yeah, there may also be applications where, again, it's going to be interacting photonics to send signals, and entangled photons can give you better performance, and then detectors and sensors to look at leakage of gases and unwanted chemicals in certain oil fields and other kinds of places. So that's an area people are working on. Other kinds of kind of field sensing, where you might have very nasty things that could leak out in certain situations, so you want to have very sensitive sensors, but you also have some large area where you need to probe, and hence having some way to have basically a grid of light being able to carry the information between different sensors. So that's things that people are looking at too.
Thank you for the feedback. So we are wrapping up this panel. I have one final curveball to throw the panelists. It's a quick, simple answer, and this is everybody's opinion only. Don't make investments based on our opinions. But quantum is really exciting as an industry because it's so emergent. We have well-established giants leading this field. We have an amazing ecosystem of startup companies developing disruptive technology. So my final question to the panelists is, who should we be watching, in your opinion? Who are going to be the disruptors across QPU or across supporting technologies. If you had to throw a vote in there and say, this is the company I'm watching and I think are going to do great things, and I'll kick us off with my vote, and I have to throw a nod towards Maybell Quantum and their dry dilution refrigeration.
In quantum networking, it's Aliro, A-L-I-R-O. It's my job, folks, sorry.
Yeah, I'll echo that. Scientific Instruments, no, but Amazon, I would say.
Hey, all right.
There's many great quantum sensing companies. Happy to talk to people at Copy. I won't just pitch mine, so I won't say that, or the ones I'm involved with. Euclid, ARC, Quantum Catalyzer. Okay, I won't just pitch them. But in other areas, I'm really impressed with what IonQ is doing, not just with their core technology, but with smart acquisitions that are integrating sometimes technological add-ons that can enhance what they're doing, their roadmap, and diversification into, networking to link computers, but I think they're going to do more than that in their first quantum sensing timing acquisition, Vector Atomic. I'm also a big fan of Quera, the spin out of Harvard. I know all the founders very well. They're my former colleagues. And I think for quantum simulation tasks, that the Rydberg atom array approach that Quera, some other companies, I want to try to mention them all, Atom Computing, Pascal, et cetera, all of them are very interesting, and that's, I think, something to keep your eye on, too.
Appreciate all of the opinions there on front runners to watch. We are out of time. Thank you all very much for listening to our panel today.